All right. Today's question, have you split up? You can tell some of these I'm really stretching. There he is. Boom. All right. So today we're learning to solve differential equations. We'll be successful when we can solve more differential equations by separating variables. So today is basically just an extension of what we did the other day in 5.6. It's just we're still separating variables. It's just not we're not always directly relating it to exponential, like to growth or decay. They're just let's solve by separating. So separation of variables. These are differential equations. These look a little bit different than some of the ones we looked at yesterday, or the other day, 2 days ago. But these are still differential equations because they contain a differential, at least one. Our goal here is we're going to try to talk about what's the difference between general solutions and particular solutions. But here are some original differential equations. If I was to separate the variables so I could start integrating to get rid of the differentials, they would look like this. Again, try to get everything with one variable on one side and one variable on the other side. One thing I want to point out is that sometimes differential equation will have like a y prime in it, something like that. Depending on how many other variables there are, you may or may not want to rewrite that as dy dx. In this case, since there's x's, I probably want to rewrite y prime as dy dx. And that's why they got dy equals cotangent of x dx, because you divide by sine of x, sine or cosine divided by sine is cotangent. That's how this one appeared. This one, again, this is e to the y. So we just divided by x, turned y prime to dy over dx, multiplied by dx, so we could get this one over here. So more or less what we're adding into the separation of variables is that maybe you have to subtract something first before you divide or multiply to get rid of things. So that's kind of the extra little piece today. It's just like maybe you have to add or subtract. Now there are a couple other little things that we're going to look at today. In particular, general solutions versus particular solutions. Again, I keep mentioning it before I'm ready for it because I just want to talk about it. Here's another differential equation in blue. Y prime plus 2y equals 0. If I went through and actually solved that, I would get y equals c times e to the 2x. That is a general solution because I have a constant in there. That's c. Because that constant is there, it's a general solution. A particular solution, the c is not there. In fact, c is 1 in this case. A particular solution you can't get unless you have an initial condition. You have a value of x and y or whatever the variables happen to be. Again, typically we use x and y for these, but it doesn't have to be. But again, in order to get a particular solution, you need to have an initial point to use. What you do then is you plug in the x and y values and solve for c. So that is how you get a particular solution. You plug in a known value and solve for the constant. Oh, yep, that's what I was had there. So again, both these are solutions to this differential equation. You could plug them both in and you would see that they would work. But the particular solution is solved for the given information. Again, if you're not given information, if you don't have any given information, then it is just a general solution and you're done. So fun fact, so taking an acceleration equation and getting the position function is solving a second order differential equation. Good job. And by second order, I mean you're involving a second derivative. Because acceleration is the second derivative of position. So if you were to solve that, you would end up doing two antiderivatives, technically, to get there. But solving a differential equation, again, just means getting rid of the differentials, which we, again, do by integrating. So here is something else. Oh, I just meant, here's the order. So the order of a differential equation is the highest order derivative. So here's an example of something that you might see in your practice tonight. Wink, nudge, elbow. So determine whether or not each of these given functions is a solution of the differential equation. Now, this differential equation right here is a second order differential equation because there's a second derivative right there, y double prime. Now, if it's a solution, I should be able to plug the function in and its derivatives, and it should satisfy the equation. It just, now instead of just plugging in like a value, we're plugging in a whole function to see what happens. So we're going to check each of these together. Again, you have each of these boxes. So again, we need to check to see if this equation satisfies the differential equation. So we need to find the second derivative of this as well. So the first derivative is cosine of x. The second derivative is negative sine of x then. So if I take the first derivative and the second derivative and plug them into the differential equation and follow along, I get negative 2 sine of x equals 0. No, that does not satisfy that equation. If it was to satisfy the equation, it would be 0 equals 0. So that is not a solution. Excuse me. By the way, sine of x would be a particular solution because there's no extra constants in there or anything. So that's trying to show a particular solution is or is not a solution to a differential equation. So there will be some in this particular practice where you're not trying to actually solve it. You're trying to verify that it's a solution or not. All right, let's have that one. Boop. All right, let's check on this one, see if this one works. So the first derivative, and if you don't see it, it's to the negative x up here. So just a thing to make sure you're aware of. So I have y prime is negative 4 e to the negative x. That's why that's negative, because e to the negative x, derivative of e to the x is just e to the x. But derivative of e to the negative x is negative e to the negative x. So y prime is negative 4 e to the negative x, which means y double prime is 4 times e to the negative x. So here's y double prime. Let's plug them in to the second order differential equation and see what we get. So when I plug them in, again, y double prime is 4e to the negative x. And then I have 4e to the negative x. I get 0 equals 0. So this is a solution to our differential equation. By the way, this is a particular solution. There's no extra constant in here. There's a defined number to be here. So this is showing a specific solution a specific solution is a solution for a differential equation. Boop. C. Notice this one looks almost identical, except there's a C here. So this is a potential general solution to this differential equation. Well, this is C times e to the x. So the derivative is C times e to the x, which means the second derivative is C times e to the x. So now that I have the original function, the second derivative, I can plug them in, and I get 0 equals 0 again. So this is also a solution to this differential equation. Before I go too much further, what questions do you have at this point about anything we've mentioned so far? Because I can keep going, but I'd rather just take a question or two. from anybody? Just finding my mouse, moving that over here so I can see it better. Okay. All right. So again, what we just did was verifying solutions. There's a slightly more complex one here. It's a little bit easier to see if you just pull up the presentation yourself rather than you looking at it. Or in the room, it's hard for me to see it. Like this color right here, while awesome, I can't really see it right now. So to verify solutions, make sure to get the different derivatives that you need, then substitute them into the differential equation. If you need a particular solution, use the given information after verifying the solution. So there's more, if you check the post credits, you can see more work for this problem. But again, like, so if you have a problem like this, hint, nudge, elbow, you might have something like this. Verify the solution works first, the general solution. So we're saying that this right here, let me just use this bad boy. Y equals C1 times X plus C2 times X to the third. I'm saying this is a general solution. Verify the general solution works first by finding the first, second derivative and plug them in and see that it does in fact work. After that, using the three different equations that you have, start trying to solve for C1 and C2. Now, because they're labeled C1 and C2, that means they have different values. Okay? So you will get two different constants when you sit down and start working through those different little pieces. And again, it should work out. When I say verify, it doesn't mean that it may or may not be. It is the solution. You just have to show that, like, more or less the algebra and calculus that is in fact the solution. But that's it. This, again, like I could walk through more, but it's easy. There's a lot more learning to be done if you start jumping into it first, and then I answer your questions about it a little bit later. So I'm gonna pretty much wrap it up with that because I want to give you a bunch of time to work so you can ask questions to kind of wrap your mind around things that are going on. Is it just those 5? Maybe it was just those 5. The way I set it up looks very suspicious. Oh, yep, low key. 5.7 is 5 problems. Also, I wanted to point this out that if you start with position as your original function, that the first derivative is velocity, the second derivative is acceleration, the third derivative is called jerk, the fourth derivative you either call jounce or snap. I go in with snap because then it's snap, crackle, pop. The seventh derivative is lock, the eighth derivative is drop. Fun facts. And you can go the other way, the antiderivatives, but all these, I don't know, I think those all suck. But I think these are super awesome. I love the fact that the third derivative is jerk. It basically is just like how acceleration changes. So what does that mean in person? I don't know.
So like being jerked around.
Like a jounce? What is a jounce?
Nice.
A jounce is like the acceleration of acceleration.
I totally understand.
Insane.
Like how's the growth or how's the change of acceleration changing? Like how much real world application do a lot of these have? I don't know. I asked Mr. Kelly about it a while ago and he's like, yeah, I don't think I've ever used anything more than a third derivative. Like jerk sometimes shows up, but a lot of these don't show up in pretty much any applications. I think I searched really hard and they kind of think about the third or fourth derivative when making roller coasters, but that's about it. I just know they're defined, and I think that's really awesome that they're defined. But yeah, the actual use, no idea. No idea. I don't think there is tons of use for it. Oh, I'm gonna stop.